since I started working in the industry, microprocessors have got around 10,000 times faster. So this talk is basically about that, and will it happen again? Will you get 10,000 times from where we are now? So how did it happen? How did we get microprocessors that were 10,000 times faster? Well, it's all down to the so-called Moore's law, the observation that Gordon Moore made while he was at Intel, simply pointing out that through enhanced processing, better bits of engineering, you could fit more transistors on the same area of silicon. Now, it's not a law in the sense of an actual science thing. It's an empirical observation. He just said, well, this seems to be what's happening. Nowadays, it's a self-fulfilling prophecy. So the International Technology Roadmap for Semiconductors treat fulfilling Moore's law as their raison d'etre. So you have a $300 billion industry that is trying to fulfill Moore's law. And they bend materials science and really arcane bits of technology to make it happen. And they've been doing quite well. Since the 1970s sort of era, they really have been on track for keeping the law running, albeit we had to change the words of the law a few times along the way. When you first propounded the law, it wasn't double every 2 years, it was double every year. Then he adjusted it to a year and a half, and now 2 years. It will keep running for some variation of that. So what does it mean, the law? We can have more transistors in a given area. So on the wall behind me is a plot of ARM1, and in my hand is a piece of paper bearing a plot to the same scale of Cortex M0 Plus in today's 20 nanometer process. It's about 70,000 times smaller in area. So that's basically what it means. We can have a microprocessor, fairly decent microprocessor, and we can make it jolly small. Alternatively, we can spend lots of transistors on doing things. So what does that bit mean? What does spending transistors on implementing microprocessors mean? What's it all about? What are transistors? How do we use them? So on the left-hand side of the picture is a die shot of the 6502. It's full of wild colors. The wild colors are real in one sense and unreal in another. We've done the wild colors by shining very bright lights onto the silicon, and so we get all sorts of diffraction and refraction effects. So where we have fine metal gratings, we get some diffraction. Where we have pieces of silicon, we can refract the light through it and get different colors. So you can see that there's a green blob here. That's the 6502's instruction decoder, and that green, it's got a fine mesh of metal across it. And there's some yellow at the top. That's silicon, bulk silicon with light being refracted through it. So the nice colors, we try and make it happen, but it's fake. If you look at a piece of silicon, particularly nowadays, it's this copper-colored dull slab without any fancy colors. So everything on here is built out of transistors. Uniquely, on the right, we have the circuit diagram of the 6502, the actual thing the engineers built, and we've topologically distorted that to match the die shot. So you can see this bright green thing is this thing here, full of dots and rows, and that is, as I said before, the 6502's instruction decoder. And you can see structures around, but it's not really my purpose to tell you how to design a microprocessor, because that's my job. So what do we get with 4,000 transistors? We won't have to look at circuit diagrams for the rest of the presentation. We'll be looking at block diagrams. So on the right is a block diagram of the 6502 in the original data book published all those years ago in 1974. And you get a sequence of blocks connected by either thin lines or thick lines. Thick lines represents a bus with more than one bit on it, thin lines just a bit, and the blocks are variously processor registers or function units. So that's what a microprocessor is. It's a set of function units connected by buses with signals going along it to cause things to happen. So with the 6502, we had transistors that were fast enough to make it run at 2 megahertz when we built the BBC computer. 2 megahertz doesn't sound like a lot now, but it was quite fast back then. It could do 8-bit operations, so the size of these buses is 8 bits, and it would take 2 clock cycles to do the fastest operation it was capable of. So add immediate 9 to the accumulator with carry was a fundamental operation of the 6502, and that would take 2 clock ticks, 1 microsecond. The thing was 21 square millimeters in size, a relative giant, but then it was built back in the day when we called the process 6 micron. You'll notice I say 6 micron. I don't mean transistors are as small as 6 micron. They're much, much bigger than the smallest feature size on a process. Back in these days, a transistor was more like 60 microns across. Huge, horrible, great big things. So that's what we got. Now, how did we use a 6502? Obviously, I spent years slaving away writing in machine code. You could do fascinating things with the 6502 in a BBC machine. Braben and Bell managed to write Elite in a BBC machine. So a full 3D graphics space trading game coded like that in those transistors. But if you're going to write a programming language, you might be interested in what it does. So the popular programming language where I come from is C. So we're going to illustrate what you have to do to get a 6502 to execute a bit of C. So the bit of C is at the top left. We've got 3 integers. Processors like linear integers. We're going to add 2 of them together to get the third. So what would a compiler spit out to make a 6502 do that? Well, it spits out this long train of things. I don't intend to go into the details of it. It's perfectly accurate 6502 machine code. You'll notice there's some repetition going on. It deals with all the addresses, then the addresses plus 1, the addresses plus 2, and the addresses plus 3. Because it's only an 8-bit machine, if it wants to add 32-bit integers together, it has to do it sequentially. So that takes it a long time. The 6502 was reckoned to be really quite a fast machine for its era. But to do this, a single statement from a high-level programming language takes it all those instructions which take 26 cycles, best case, to execute. And fundamentally, the reason is that we don't have very much storage in the machine and it can't operate on very big values at a time. So Gordon Moore waves his magic wand, we get some more transistors. We can go off and design a microprocessor using lots more transistors. What do we do? So on the left is Steve Ferber's original pencil sketch of the ARM 1. On the right is the die shot. Hasn't come out that pretty. We didn't understand the importance of positioning the lights correctly when we took this shot. You can see immediately that there's something radically different about ARM compared with the 6502, however. If I just nip back, the 6502, that's pretty much a sea of gunk, isn't it? There were some structures like the decoder, but in there it was all gunk. On ARM, it looks quite neat. There's structure in there from all sorts of levels. There's regularity. This is because ARM has been laid out with the help of a computer. The 6502 was built by people who sat in front of a big drawing board and stuck rubylith tape to translucencies to make the photomasks for it. So it was designed completely by hand. ARM was designed by people who were working with transistors directly, but with a computer to help them. So the computer likes straight lines, likes laying things out. So what do we get when we use more transistors? We used 25,000 transistors to make ARM1. We got a machine which is full of all these blocks. But this time, things are bigger, 32-bit. The buses are 32-bit. Single signals are just 1-bit, but that's fine. With a 32-bit machine, we also spent some transistors on making it just go faster. So we can not only improve the machine, give it more registers, let it handle 32-bit numbers, but we can burn transistors to make a better implementation. So where the 6502, which was quite hot for its day, uses up at least 2 cycles to do anything, we burned enough transistors on ARM1 so that it could do something in 1 cycle, by which I mean, of course, that it took at least 3. We burn transistors in a pipeline. So this machine can fetch instructions, decode instructions, and execute instructions while fetching the next instruction, decoding, and so on. So there's a pipeline. 1 instruction can be completed every clock cycle. The 6502 couldn't do that. It was the first microprocessor I ever saw with any form of pipeline. It prefetched the next instruction, but otherwise it sequenced through multiple clock cycles without running any parallelism inside. So ARM1 is relatively large, 37 square millimeters. So that's bigger than the 21 square millimeters of a 6502. Meant it was a bit more expensive. And it was built on a 3-micron smallest feature size process. So still big, hungry transistors, as you could see. I mean, the picture that we took at the time, that is a picture taken with a camera with a lens on it. There are no microscopes being used. It's big. So when we look at our piece of program, we can see that ARM has a magnificent advance over the 6502. We don't need to do 3 sets of operations. We can get everything done much quicker. Of course, ARM, which is a RISC processor, where RISC stands for Reduced Instruction Set Complexity. So it's not that ARM has fewer instructions than the 6502. It has a lot more, but the complexity of how the instructions are implemented has been reduced. So one of the things that ARM does that the 6502 doesn't is ARM restricts access to memory to just load and store instructions, and then everything else operates on internal registers. The 6502 has much more complicated instructions which actually add locations in memory directly to things. So you had all. So that in itself is 3 times faster. And I could justly claim that that was my responsibility to make it so. Of course, the fact that the transistors are so much faster, that's Gordon Moore's responsibility. So that 10,000 times performance gain is brought like that. The transistors go a lot faster, and that's most of the performance gain. And implementers like me use the transistors in smarter ways, make the pipelining work better, make the processor work better, and that's the small gain. So we could probably say out of that 10,000 times gain, 10x is down to me, and 1,000x is down to Gordon Moore. Obviously, we still make ARMs today. There are 95 billion ARM-powered chips. Each of those chips probably has more than 1 ARM core on it, so the number of ARM cores is now essentially unknown. We don't know that at all. Modern implementations of the processor, they vary from things that are as simple as the Cortex M0+, which is the nearest modern equivalent to the ARM1 that we made, all the way up to the Hurricane processor that Apple designed to run in the iPad Pro and the iPhone 7. Actually, no, iPad Pro is currently limited to Twister. Hurricane's only in the iPhone 7 until A10X comes out. So by burning lots and lots of transistors, we can speed this up by another factor of sort of 4.5. I did say that the processor architects don't do well out of this, whereas the people who give us faster transistors, they're the real heroes. So the magic wand will be waved again. What can I do if I'm given more transistors? And I want to implement a more complex instruction set. So this is what happens if I get 6 million transistors. I design a processor like the Firepath. Now, it seems to have gone back to being a gungy splurge. This processor is almost completely designed by computers. So there's none of the sort of almost anal retentive aspect of laying things out in straight lines for this. The computer just puts the transistors where it knows they'll be fastest. We have got some evidence of high levels of structure in the machine, and you can sort of see that the top and bottom of it look the same, and there's these big yellow things at the right-hand side, which are the register files. And if you think about it, those register files are now massive, because this is 6 million transistors, and I'm using a jolly good portion of them for the register files. Transistors, So what do we get? Well, for a start off, we're in a much nicer process. This was designed some time ago. It's in 0.13 micron, which at the time sounded very small, hard, difficult to design, but nowadays, so easy. We use 6 million transistors, but the transistors have got so small in the 0.13 micron process that a Firepath is only 7 square millimeters, fractions of the size of ARM1. And the transistors have got really, really fast, and we tried really, really hard to make this machine go fast. So we spent an awful lot of transistors on making it go fast, and they were fast transistors. So it runs at 330 megahertz compared with ARM1's pedestrian 8 megahertz. What it's designed to do is very different, however. ARM1 is essentially designed to run sequential programming languages. This thing is designed to run parallel stuff. So this line beginning add W, what that instructs the machine to do is one instruction, one indivisible instruction. It's not multiple instructions, it's one thing. So it says, take the register pair R2, R3, the register pair R4, R5, add them together, considering them as packed 32-bit words in a 64-bit container, twice over, and generate two 64-bit answers, R0, R1. Meanwhile, take the address in R8 and load two registers from it, R6, R7, that are 64 bits. And that's one instruction in the machine. Okay, so you can design with 6 million transistors, even if you spend a lot of them on very fast implementation and a shed load of them on doing lots of multiplies, you can design very complex instructions. You may have noticed that there's no programming language in the world that's anything like close to. If you want to program this machine, you talk in its language. You either talk in Firepath assembler, or you talk in C with intrinsics, where the intrinsics are the machine operations, and you're just using the compiler to sort of automate the register allocation and scheduling. Modern programming languages are scalar, basically. There are very few that try to be parallel at all, let alone parallel in the ways that machines like this can handle. So if we look at our piece of scalar C, well, it's a bit boring. The Firepath translates into something that looks uncannily like the ARM code. There's obviously a reason for that. We can use some of Firepath's parallelism, that the first line, LDL R0 and LDL R1, that's a single instruction to Firepath, tells it to load two different things from two different places. It's fine with doing that. But then we have sequential nature in the program that we're trying to compile, so Firepath doesn't get to use much of its parallelism. And finally, it only has one thing to store. So in a sense, Firepath isn't very at home with writing scalar C. The machine could have done that instead, where it did 4 32-bit loads and 4 32-bit multiplies in a single cycle. So Firepath is reasonably quick. The machine back in 2003 would do that in 6 cycles, which was quite performant. And it's not surprising that we could use that machine for a lot of signal processing. If you have DSL broadband come into your house, the processor that runs the DSL broadband at the other end of the line is a Firepath. So we get more transistors. What can we do with them? Even I failed to design instruction sets much more complex than that. What I can do with more transistors is to put more of them down on a piece of silicon. So this is a picture of one of the first Firepath chips, the first massively successful one that took over the world, and no, you've never heard of it. It's got 2 Firepaths on it, one here and one over here. I said about the colors. There's lots of pretty colors on here caused by diffraction and refraction. This block of stuff down at the bottom is data memory for the processors. The equivalent block of stuff at the top is instruction memory for the processors. So this chip needs no external memory. And then the stuff up there is what we call a hardware assist, and that helps us with doing crosstalk cancellation at the front end of a DSL line. But it doesn't do anything else. The rest of the functionality, making this machine run 16 lines of ADSL2 to your home, is all software. There's no other hardware in the system. So that's what happens if I'm given enough transistors to do that. In fact, we never built a Firepath-powered DSL chip without at least 2 of the things. If I'm given more transistors, therefore, my obvious step is to have more processors. So here we are a little way on. We now have 4 Firepaths. This thing's doing VDSL. It does 16 lines of VDSL2. So that's 100 megabits down to your home, 50 megabits back up. It's still, still masses of memory, processors, those little hardware accelerator things. That's what it's doing. Can I keep doing this forever? Can I keep just being given more transistors and put more Firepaths down? Oops. There's a law in the way. And this one really is a law. It's got a graph and an equation and everything. I mean, how else would you know it wasn't a law? So this is Gene Amdahl's law. It says the speed up when you use multiple processors is limited by the sequential part of the program. So if you think of your program as having a parallelizable bit and a sequential bit, and you parallelize the parallelizable bit, then the sequential bit is what slows you down. So it's kind of obvious, but it did take a genius to point it out. So the speed up for n processors is that. For those not used to looking at equations and instantly knowing what that means in real life, let's take a program that's massively parallel, something like ray tracing, often quoted as something that you do massively parallel. And it is indeed massively parallel. The tracing of a single ray through the scene is completely independent for every ray, though, of course, the scene needs to be distributed. Ray tracing is in fact, about 95% parallel. So 95% parallel is the green line. The green line starts off at one processor. As we add processors, the green line rockets up. Yeah, it's ray tracing. We can run ray tracing on parallel computers. Lovely. We keep adding parallel computers, and the green line sort of leveled off. It levels off at 20x. No matter how many processors I apply, ray tracing ain't going to go any faster than 20x faster. Well, ray tracing is a special case. It's really worth building parallel processor farms for ray tracing as a single task. Cutting to the chase, what does everybody do with their computers nowadays? They run web browsers. Web browsers have lots of parallel threads in them, don't they? They're about 2 to 4-way parallel. So that's somewhere between this light line here, that light line there says 50% parallel. Half of your work can be done in parallel and half can't. And the red line here, which is 75% parallel. 75% of your work can be done in parallel, and the rest can't. So what we're saying here is that web browsers on multiple processors sort of are capped somewhere between 2 and 4x faster than they would have been on a single processor.
So is P the percent of parallel?
Yes.
And N is the number of...
N is the number of processors, P is the percent parallel. We have a mathematician in the room. So that's kind of bad news. We're dead set on selling you smartphones with ever-increasing numbers of cores in it. This is a monster octa-core. The 10-core stuff and beyond is coming really soon now. And you will go and hand over your money to buy multi-core processors in your phone and in your tablet, if you still buy them, and in your computer. You've been buying 2 to 4-way parallel computers for quite some time. So you'll hand over your money for this stuff, and it ain't going to do you any good. If you've got lots of things to do in parallel, if you're a server farm where you've got zillions of things that are completely independent, this is good news. If you're a consumer, you're going to hand over your readies for the latest, greatest technology, and it's pretty much not going to be any good. That's a bit of a shame. There are, of course, other problems. So that's what I just said. It would be nice if you could go out and take your programming world and split it automatically across all these parallel processors that you just bought. And there's been an awful lot of research in the academia about that. For about the past 20 years, we're no closer to a good solution. So if we continue to use scalar programming languages, which we do, because people are being taught them all the time, then we have this problem that scalar programming languages simply don't fit on the machines that you're buying, that the industry is making, that we don't give you any choice about. And we can't automatically compile from a scalar representation of the problem into a parallel machine. It's proving to be enormously difficult. It would be nice if you guys went off and learned how to program parallel machines directly. But of course, just like in original eras where GOTO was considered harmful, sequential execution is considered harmful, and it's the first thing you're all taught, that a program is a menu with a series of steps that are performed in order. I mean recipe, not menu. Too much food on my mind. Well, if that were the only problem, that would be bad enough. But we do seem to have another problem. You'll have noticed when you're holding your smartphone and using it, it gets hot. We've been getting more and more power-efficient transistors all the time. But we use so many more of them that little square centimeter or so of stuff in your phone that's doing all the work gets really, really hot. So this is a graph of the power density of processors. So as we make our processor use more and more transistors, we reach the power density of a hot plate. It's not as hot as a hot plate because it's small, but it's got the power density of a hot plate. If you put your finger on one of those, it would burn straight through. Intel kept going. Even as they crawled this graph up, they kept going. They didn't quite make it to as hot as a nuclear reactor. Not quite. They tried really hard. It went badly for them. The machine that did nearly get to be as hot as the nuclear reactor was the ill-famed Pentium 4. They had to completely throw away the way they were building microprocessors and go back and start again and come down over here. So this is the beginning of the core line. So Core 2 Duo being the first of those. They literally had to stop doing it the way they were doing it and start doing it a different way, and that was because of power. Well, that's pretty bad. Maybe I shouldn't take a bet on the industry getting a lot better in the future. So we're going to go on putting more transistors into the space. And now we're going to sell you more and more complicated machines with more and more transistors in use, and they're going to get really, really hot. And to stop them melting, we're going to turn them off. So you're going to buy the 10-way, 18-way multi-core processor that's the latest thing because we told you could buy it and made it available. And we're going to turn some of those processors off most of the time. So you're going to pay for the logic, and we're going to turn it off so you can't use it. So as we go forward, even as we've moved from ordinary planar transistors to these things called FinFETs, we made transistors better. So transistors used to be flat. So we used to have depletion layers in the silicon. We used to slap a metal gate on top of it, and that was a transistor. So as we put a charge into the metal gate, current would or would not flow across the depletion layer, depending on what charge we used. And that was getting really leaky. So nowadays, we make a transistor vertical. So this is the transistor, and then we wrap the gate around it. So we've got a much bigger effective gate size. So with FinFETs, we got better transistors that leak less and didn't get as hot, but we still use more of them, and it still gets hot. So 7 nanometer is right around the corner in 2020. We're going to have to turn half of them off. So we're going to sell you a die that's the maximum envelope that will fit in a desktop computer at 125 watts, and we're going to have to turn half of it off, otherwise it will melt. That is going to be fun. Now, the industry, you may have noticed, is trying to get denser still and do 3D stacking. Well, that creates even hotter hotspots where you have to turn more of it off. Obviously, this already afflicts your phone. Your phone only has about a 2 to 3 watt TDP for the processor, so it gets turned off most of the time. One of the most expensive processors you'll ever buy and not use. Oh, no, not another problem. It's getting really expensive to do this stuff. So we don't have any physical limits. There's no scientist coming along and saying, we can't scale things down. What we do have is a bunch of people, a bunch of engineers saying, it's getting really expensive to do this stuff. 28 nanometer, a set of masks costs $5 million. 20 nanometer, 14 nanometer, now in production. Intel, Apple, and Samsung are all in bulk production at 14 nanometer. Third-party chip companies like NVIDIA, AMD have just started using 14 nanometer FinFETs in their latest things built by TSMC. And you may have noticed that these things have come onto the market, particularly if you've looked at NVIDIA pricing and discarding any distortions in the pound-dollar ratio at Brexit. You may have noticed these things are more expensive than the things they replaced. This is because the transistors themselves on the smaller processors, they're better transistors, sure, but they're more expensive transistors. It's got so expensive to do the processing on a piece of silicon that the transistors themselves actually cost more. So we get a better thing. The A10 is built by TSMC for Apple. It uses these lovely FinFET transistors that turn on and off better. Apple have been able to ramp the speed of Hurricane up compared with Twister and use more transistors and turn on more transistors without power problems, but it costs more. So we're obviously going to work on it and deal with the processing, and I could describe the arcane things that we do to even get this far, but the takeaway is this is sort of the end of Moore's law. Only a few things are going to be worth the greater expense of process geometries. Smartphone apps processors, yes. IoT device, no. Will you find your Arduino built with a 7 nanometer FinFET device? Probably not. The volume's just not enough to make it worthwhile. So for Internet of Things and cheap devices, the economic picture looks like 28 nanometers forever. This is a rather dense slide with lots of information. This is from TSMC. And what it basically says is, as we come down the process geometry size, we obligingly get more and more gates per square millimeter, down to 7 nanometer, where you get 17 million gates per square millimeter. So 1 square millimeter, 17 million gates, or as I like to think of it, 3 Firepaths. We have difficulty packing them together, so you can see the gate utilization has fallen. This is because the rules we have to obey to get the thing manufactured are so much harsher. So the used gates aren't scaling as rapidly. And we can also see the cost per gate. It fell to a minimum in 28 and is beginning to rise again. That's really bad. So as we look forward, here's next year, 2017, we'll be seeing only a few things left on 20. Most people transit into 16, but instead of 16 going up in volume across the industry, it's falling. And 28 lives on. So better get used to making things in 28. So predictions are very hard to make, especially about the future. In April 2002, the head of Intel, who must surely have known a bit, predicted that they'd have 30 gigahertz, 10 billion transistor processors by 2010. You'll have noticed that we didn't have that. And in this presentation, we've seen a few reasons why it didn't happen. And there again is their turn off to the side when the power density got too much for them at the clock frequency. So they never managed to get even close to it. In 2006, I bought a laptop. It had a Core 2 Duo in it. It ran at 2 gigahertz. That's pretty much the state of the art today. So conclusions from all of this. Well, we're going to get more transistors. We can have increasingly specialized, smartphones that fall to the floor, increasingly specialized microprocessors fit for purpose. You've all got used to the fact that you buy something and it will have a CPU, a GPU. If you've bought a phone, there'll be DSPs running the baseband and all sorts of other things sitting around. So you buy a big sea of heterogeneous processors. And that's great, because it's a lot of work for people like me and for system-on-chip designers, and a lot of work for people like you, programming and herding all these beasts together. But even so, performance related to parallel or special purpose programming only going up, users of computers will have to adjust their expectations. The gain I saw in my lifetime, 10,000x increase in scalar performance, this is not going to be repeated. And we're going to have to pay more for our toys, doubly more for our toys with Brexit. So that's the end of the talk. QE machine, there we are. So here we have a microprocessor actually executing stuff. And it's at this sort of time that you can just gaze in wonder at it. This is an ARM1, and the tracers light up as signals stimulate them. So that's the end of the formal bit, but you can ask questions.
Yeah, that works. What is it that has stopped? Do you know what the economic factors are that have stopped the manufacturing density from continuing to shrink?
So we're making things with conventional ultraviolet lithography. Well, in fact, deep ultraviolet lithography. So, we're working on processors that have transistors built out of elements where we want to resolve down to the nominal process number. So 14 nanometer, 7 nanometer structures. And we're doing it with 193 nanometer light. So that's really quite big. It's far bigger than the structures we want to resolve. So we're having to use multiple steps of lithography to make those features. So that's what's causing this explosion. Now, the thing to the rescue that hadn't happened for about the last 15 years is extreme ultraviolet lithography. where we use shorter wavelengths of light. And the reason that hasn't happened is we require about 125 watts per square centimetre to expose the masks through the photomasks in the photolithography step. 125 watts of extreme ultraviolet is very difficult to produce. I'll give you an idea of what happens because I think of this as more like a laser space weapon from Star Wars. To build an extreme ultraviolet source, we build a vacuum chamber, we scatter molten tin into it, we excite it with a low frequency laser and zap another laser off it to vaporize the molten tin that's in space, and the beam that comes off that is then collimated and it has extreme ultraviolet, so we pass it through a beam splitter to split that bit off, and we're expected to get 125 watts per square centimetre of light illumination out of that. So I did say there were some arcane things going on. We haven't been able to get that up to capability so far. People are working on it quite hard. The semiconductor market is $300 billion per year. So there's a strong incentive to get this thing right. When it comes along, it will be far too large for probably 7 nanometer chips to be made with it. So we'll still have to have multiple masks. But we just don't need as many. We're using 4 at the moment. We'll probably be able to drop to 2. But the light source is really expensive, so it have to be paid for.
Hi. Do you think there's a chance that we'd ever see a non-silicon microprocessor at all? Or?
Well, microprocessors, although we call them silicon, they're mostly other things. Silicon is acting as a base to create some sort of semiconducting medium on which we slap a lot of other materials. So we're looking forward, and we'll use other materials in the bulk silicon. So for 1 nanometer, somebody's made a single 1 nanometer transistor, and that is a large amount of bulk silicon, a molybdenum disulfide gate on top of, layer on top of it to form the depletion layer, where in bulk silicon with CMOS today, we diffuse different substances into the silicon to create an N and a P. But now we're going to use bulk silicon and a single layer of molybdenum disulfide, and then a carbon nanotube through the bulk silicon to be the gate. So we will have to be molybdenum disulfide valley. But it will really be bulk silicon. Silicon has excellent properties for handling. Any other questions? There's a man down the front.
Additiva just recently announced the 1,000 core coprocessor, the Epiphany chip. I'd love to have your view on that in general, and around coprocessors in general.
Yeah, I mean, so parallel processing is a thing. There are many problems, such as deep learning, where parallel processors work quite well. They're fundamentally parallel. Your brain is fundamentally parallel. And we can use a lot like that, but they're only in special purpose zones. The people who have the biggest numbers of microprocessors on chip are collectively the Human Brain Project in Europe and the equivalent one in the States. So IBM's True North chip has 250,000 processors on there. Each processor is designed to simulate a spiking neuron, such as your brain does. The Spinnaker project in the Human Brain Project in Europe is doing much the same thing, but they are using programmable microprocessors so they can vary the model of the neuron. IBM's neuron is hardwired, and Spinnaker's isn't. Both people have made million neuron systems, and they can train those things. At a million neurons, you're sort of at cat level of intelligence. A single Spinnaker chip is sort of a fruit fly. A board full of Spinnaker chips is heading towards being Drosophila. No, I've got the wrong ones there. It's a small tapeworm by the time you've got a board full. And then you need a whole rack full to be a mouse. You'll see a lot of things happen in learning systems in the future, but of course you won't be able to run Erlang or C on them.
I guess this is the last one.
Is that what's driving this then? Deep learning stuff, do you think? Because otherwise it sounds like a bit of a vanity project to get yet more transistors into less and less space that we can't use.
It's one of the areas where there's significant hope. We're still learning about how to make these things, so there are big design changes going on inside GPUs in particular. NVIDIA, a few years back, started making GPUs in a different way. That made them much more power efficient. They've kept that advantage over AMD as big GPUs ever since. AMD is sort of groping towards the same type of technology. Signal processing, digital signal processors like Firepath, we're also able to make better and better ones of those, and they're far down the energy consumption scale. Things like Firepath do their work stopping far less energy than a general purpose computer. They don't have cache hierarchies, for example, and that burns a lot of power.
I guess if there's one more question, otherwise we'll close and say thanks to Sophie for an amazing talk.